So this is lecture 2, and this lecture is going to be about basically our discovery, a very, very quick introduction to our discovery of our place in the universe. So specifically the Copernican Revolution and the process by which we basically figured out that the Earth orbits the Sun. And as soon as you have that, that really sort of blows the doors off our conceptions about where we sit in the universe. This movie that's playing in the background is something that was produced by the Museum of Natural History. And you can find it, if you want me to show you where you can find a copy of this online, I can do that for you. But it's really an amazing thing because it puts together a lot of real data that we have about the Earth, the other planets orbiting the Sun, and it puts everything into scale. So what you're seeing now is a fly-through in this movie. It started off at the Himalayas and backed out, and it showed the planets orbiting the Sun. And now it's zooming out past our galaxy now, and every one of these little green dots is actually another galaxy and these galaxies fill the universe. And so what this represents is one of the largest maps, real maps of the universe that we've ever made. So this is a real map of galaxies. The reason why it has this weird shape is just it's a selection effect. It's just the part of the universe we've been able to survey. And then what's coming out now is this kind of green ball is basically the edge out to which we can see. It's not the edge of the universe, but it's basically the limit out to which we can see in the age of the universe. It's the distance light could have traveled in the age of the universe, more or less. And so we live in a vast, vast universe that's filled with billions of galaxies. And the start of this lecture will be sort of tippy-toeing into how we got this picture. So how we were able to develop this picture based on simple reasoning and then eventually technological innovations that allowed us to do this. And the other thing that I will talk about then after that, something that I didn't get to last time, is thinking about life and how we define life in this quest to sort of understand life throughout this whole giant universe of ours. Yeah?
So in that image, I see that we have more information regarding like the two areas and the other two are kind of more empty-ish. Is there a reason why we have more understanding?
Yeah, so I was trying to say this before, that basically there's just parts of the sky we haven't studied in great detail. So what you're seeing is, you see these sort of like bands that cut across the image. Think of a telescope, like, literally what's going on is someone has a telescope, or a group of people have telescopes, and they're pointed at one spot in the sky, and effectively you drag it over and measure as much as you can along a very teeny tiny line. I mean, if you've ever looked through a pair of binoculars, you know how the field of view is small, and you got to kind of like find the thing you're looking for. It's like that with these big telescopes. They tend to have very, very small pieces of the sky that they can see very well. In order to map out big regions of the sky, you're basically going here, and then here, and then here, and then here. So basically, we just haven't mapped out the whole universe to that depth yet, although there are plans right now to do that better. Another part of it that makes it difficult is we live in a disk of stars. We live in this Milky Way galaxy that's a disk. And it's easy to see stuff that's, if you're in the disk like this, it's easy to see stuff up here and down there, but stuff that's kind of in the same direction as the plane of the disk is hard to see. And so sort of our view of the universe is actually blocked along the directions of the galaxy that we're sitting in, but we can see out of it and into it. And so when you see maps like this, they're a little bit deceptive because they're trying to be realistic and show you real data. It looks like the universe has these big gaps in it, but we think that's just a limitation of what we can see. Okay? That was a good question. We'll come back to this kind of stuff later in the course. So part one then is what we're going to call the Copernican Revolution. And this was attributed to Copernicus, this idea that the Sun is actually at the center of the solar system and the planets orbit around the Sun. It's a pretty radical idea, actually, because, in fact, if you think about what the universe looks like, that is, what the universe looks like to you, okay, if you go outside on a clear day and you look around, the world, okay, the universe that you see, that you're sort of out in, actually looks something like this, right? I mean, when I go outside and look around, it looks like the sky is a dome. I'm sitting on flat land, and it looks like there's basically an edge. And so at some level, the universe, as we see it, right, from here on Earth, basically it looks like we're in the middle of a giant snow globe. And in fact, this idea that the universe was basically flat ground, canopied by sort of an arching sky, is something that a lot of people sort of took for granted for thousands of years. As far as we can tell, many, many ancient cultures basically had this idea that this is pretty much what the universe was like. And in fact, you know, if you think about it a little bit, and imagine that you've never seen pictures of the Earth from space, right? You don't have the ability to travel really long distances. This is not a bad starting point. In fact, this is kind of what it looks like. Okay. And it's interesting to ask yourself, you know, let's say you were transported back in time, you know, 4,000 years ago, and you could somehow talk to people. Imagine they could speak English somehow. How would you convince them that this was wrong? Okay. Does anyone have any ideas? What would you say? You can be like, believe. Sorry? Okay. What does that mean? What do you mean by math?
I don't know. I'm not a physics major.
You don't have to be a physics major. Yeah. These people you're talking to aren't physics majors either. There's no physics 4,000 years ago. Why do you believe that this is true? Okay, why not?
Placement of the sun differs. When it rises, like we say, oh, moon.
The moon?
Yeah.
Okay. All right. So we got the moon is doing this. They say, yeah, the moon. Yeah, we got the moon. We figured out the moon. The moon is a thing, and it goes around us like this. Sometimes we can see it in the day. Sometimes we can see it in the night. But you're not convincing me. First of all, you tell me from the future. I'm not buying that. And second of all, you tell me that what I see with my naked eye, it doesn't make sense, right? Any other ideas? Yeah.
Go on top of any building and look at the next capital over. You can't see it.
Go on top of any building and look out to the next.
To the next city. You can't see the next city over.
Okay, so first of all, it's 4,000 years ago. But we'll pretend there's some big cities. There probably were some reasonable towns.
There's got to be some capital city, and the next capital city over, you can't see it.
Well, it's because it's far away.
Exactly, but it's because the world is round. If it was flat, you'd be able to see it.
But if something's really far away, it's hard to see. Like I'm playing the role of someone 4,000 years ago, right? I mean, if something goes really far away, it's hard to see, whether it's flat or round, right?
It's not hard to see. It's invisible. It's not there.
So now I'm going to start thinking you're crazy. You're telling me that things are invisible when they're really far away, right? I mean, I'm just playing with you, right? I'm not trying to be a jerk. I'm just trying to say, look, I'm someone living 4,000 years ago. You're telling me that I live on something that's round, which clearly doesn't look round. I see this, and you say, yeah, but the reason why you can't see stuff that's really far away is because the Earth is round. And my answer to that would be, well, when stuff is really far away, it's hard to see because it's dim. It's hard to see when stuff is far away. Any other ideas? Yeah?
Ships going over the horizon and kind of sink down.
Okay. All right. I have a secret suspicion that you've heard this before, but this is what she said. She said, well, let's say you're standing somewhere and you're near the water. And we've invented boats. Okay, let's say we're an advanced civilization 4,000 years ago that's invented seafaring boats. And they sail out into the horizon. As I watch them sail out in the horizon, the last thing I see of them is the tip of their sail. The first thing I can't see is their hull. Then I can't see their middle of their sail. And then finally, it's the very top tip of their sail that I can't see anymore. So if you look at that, it actually looks like they're curving off in the horizon. That's good. That's very good. I have a sinking suspicion that you've heard that somewhere before. People get that? That's a pretty subtle argument, right? But, you know, and it's kind of the same thing where it's like, imagine you're hiking with your friends and you're up on a mountain and you got someone who's going fast, you're tired, you're like lagging behind, and your friend is out in front of you. If they go down a hill, the last thing you'll see is their head go down, right? Their feet will disappear and then their head will go down. That's sort of what distant ships look like when they sail off in the horizon. Okay? That's a pretty subtle argument. And again, then someone 4,000 years ago would say, well, then why doesn't the water just like run off? Why is there even water? If it's all tilted like that, it would just slosh away. You know, you can imagine an argument back to you that would be like, well, that's insane. Like, how is water curving off? It would just roll off. You know, you're telling me it's like a ball. If I pour water on a ball, it just rolls off the other side. Right? So the point of this is to make the case that this is not a dumb idea, right? And it takes a lot of sort of discussion and thought to disprove even this idea, which is ludicrous, right, to us now. This is ludicrous. Okay. So the first person that really wrote this is he was not the first person to come up with arguments against this, the idea, arguments for the Earth being a sphere, but he is the first person we have sort of recorded information of him writing down specific reasons for why he thought the Earth was spherical on physical grounds, and that's Aristotle. Okay, we'll hear Aristotle's name a lot in this course because in many, many areas of sort of proto-science, he is a really key figure. He just had so many ideas and so many thoughts about so many things, and he ended up being wrong about almost all of them. But he was such an influential, and his strength of argument was really, really impressive. It was more about the arguments that he had than the actual answers that he came up with. But basically, he argued that the Earth, in fact, is a sphere and is not flat. Roughly, 350 BC. He had a few reasons for this, and one of them was the ship, but another one was this one. And this is a pretty interesting argument. So imagine we lived in a universe that was like a giant snow globe, okay? Or even like this room, okay? It's sort of like this room, except the room has an arching ceiling, right? From anywhere in this room, you can see anything on the ceiling, okay? If you're in that corner of the room, you can see this light. If you're in that corner of the room, you can see this light. I can see it. We can all see it. Doesn't matter where you are. But Aristotle said that's actually not true with the stars in the sky. There are certain stars and constellations that you can see from some cities that you cannot see from other cities. Now, you would have to have traveled pretty long distance to be able to do this, but not impossibly far distances to do it. Okay? So his argument was, like, look, there's some star, some constellation over here, that here I am in Athens, I can't see this. But if I travel, say, farther north or farther south, I can suddenly see a constellation I've never seen before. And his argument was, what's going on is our horizon is limited by where we are on the surface of this spherical thing. And so when we're over here, okay, we can only see out to here because the line of sight from this star is blocked by the curving Earth. Okay, it's sort of like your idea about the buildings, being up on a building and looking for a distant city. It's sort of like that idea, except now we have a star which is so bright that I know we can see it from Earth. Okay? Any questions about this? A second idea, a second point that he made was that when you look at the moon during an eclipse, okay, during a lunar eclipse, so when the Earth is blocking the sun's light from the moon, it always casts a shadow that's round. So first of all, there's something to sort of think about here. He understood what was going on during a lunar eclipse. He knew that the Earth was casting a shadow onto the sun. He did not think it was some magical thing, right, or it was a bad omen. He said, look, there's something physical going on. You've got the sun. We know it's over here in this part of the sky. And it looks like there's just a shadow being cast here. The ancient Greeks understood this pretty well. And the point is that if you have something that always casts a round shadow that looks like a circle, the only thing that always casts a round shadow, no matter what the light source is a sphere. So he said, therefore, this thing here, that's a shadow of the Earth. And it looks pretty round. Does that make sense? And finally, it's this thing about ships that we've already talked about. He sort of wrote this down, that if you watch a ship sail out on the horizon, the sail always dips below the horizon after the hull of the ship goes down, as if it's rolling down like this. Now, all of these arguments are reasonable arguments, but they're still suggesting something that's absolutely crazy. Okay? He is suggesting, okay, imagine you're talking to your person 4,000 years ago, or in this case, 2,500 years ago, 2,300 years ago. You're talking to some people who have this sort of intuitive, reasonable impression that they live on a flat Earth, and you're telling them, no, it's a ball. How crazy does that sound? You live on a ball. Okay? Now, if you've seen ants crawling around on a ball, but ants on top of the ball do okay, but ants on this side of the ball fall off. So what is it? Why are we not falling off or sliding off? Why, when the ship sails off, if it's really going around a bend, why doesn't the water just spill off over the horizon too? Like, this doesn't make any sense. Now, how do we understand why doesn't that happen? What's the answer? Gravity. Great. Gravity. The word gravity in that context did not exist to these people. And in fact, it didn't exist to Aristotle either. Aristotle had a different answer. He said, I have an answer for this. My answer is that all the material that makes up the Earth, everything down here, including us, all this stuff, is made of something that has a tendency to fall towards the center of the universe from all directions. And that creates a little bit of a symmetry. So if you started off something that makes up the Earth and put it up really far away, eventually, over time, it would settle down and find its place here. However, everything up there in the heavens is different, and that's why it's up there. Everything up there in the heavens is made of something called ether, and ether is special. It's the fifth essence. It's totally different than everything else, and it stays up there uncorruptible and perfect. While we down here are sort of the stuff, the dregs, that has fallen down to sort of the gutter of the universe down here at the core. Okay? So the heavens, that is the stars, the planets, all that stuff is made of this ether. The Earth is fixed and does not move. And all of these things up in the sky, they orbit over our heads. Does that make sense? Are there questions about this? Now, let me remind you, and the ancient people knew this because, again, they didn't have TV or anything to watch at night, right? They went outside, they looked up the sky, and they would see the stars every night rise up and set over their heads like this. And of course, the sun would do that every morning. And you have to explain this if the Earth is fixed. And of course, the solution of to this was that all of these things are orbiting about the Earth, are rotating about the Earth. In Aristotle's picture, they were going around, they were fixed to what were called crystalline spheres, okay, that were in basically concentric spheres that went out. They were all orbiting around the Earth, this fixed point. Now, if you tried to tell Aristotle that this picture was wrong, good luck convincing him. Okay? Now imagine you're having a conversation with Aristotle 2,300 years ago, and you're trying to convince him that this picture is wrong. You're not dealing with the schlub here, right? You're dealing with Aristotle. How do you convince him that he's wrong? Now you might say, look, that's not what's going on. What's going on is the Earth is going around the sun. And he would say, that can't possibly be true. And it's not because I just don't believe it's reasonable. It's because I have a verified observational test that shows that your idea that the Earth goes around the sun is totally wrong. What was that idea? Okay? So here's what Aristotle said. He said, look, I've heard some crazy people out there talk about how the Earth might go around the sun. And in fact, there were people out there living in his day, roughly, that had this idea. And he dismissed it. And the reason why he dismissed it, he said this, look, if the Earth is moving, okay, I should be able to see it. I'm up here moving around, right? And I see all you people here. But I can tell I'm moving, not just because my ears tell me I'm moving, but because if I watch you, you are moving relative to each other as I move. Okay, so watch this. Everybody watch me. and line up to something in front of you. If you're in the front row, sorry. But if you're like back here, notice how I move compared to the person's head in front of you. Right? You see how much I'm moving? The person right in front of you is just sitting there, and I'm moving relative to that. And if you turn your head from side to side to watch me, you'll even see people in front, the positions of their heads relative to each other and me shift. That effect is called parallax. And you see it all the time. Like if you're in a train, right, going in a train, looking out the window, the stuff that's nearby you is flying by really quickly. And that's why you basically know you're a moving train. Right? Or on you ever been on an airplane, like on the runway or something, you're not really sure if you're moving, you're like half asleep. And you look out the window, you see stuff move, you can tell you're moving that way. You can't feel it, you just see it, because you're moving with respect to other things. So he basically said, look, if the Earth is moving, if I watch a distant star, okay, at one time of the year, I'll point at it and it's right there. And then 6 months later, I'll be over here, and when I point at it, it's not there anymore, it's there. So I have to turn my head to look at distant stars relative to each other as I move. And stars that are nearby will move more in my field of view than stars that are far away, right? So if I point to somebody in the front row, I've got to move, I've got to change my point a lot. But if I point to someone in the far back, I don't have to change my point very much. So this idea of motion as you move through a field of stars should be visible. And that was never observed. Do people have a question about what I'm trying to say? If the Earth's moving, you should be able to see it. Just in the same, also imagine you're walking through the forest, right? And you've got a tree near you and a tree that's far away. The trees that near you will move by quickly. The trees that are far away will look fixed. So the motions of the positions of those trees relative to each other in your viewpoint will shift around. Does that make sense? This effect called parallax is used by video game designers all the time to give you the sensation that you're like moving through some three-dimensional space. Okay. So specifically what he said is, look, if you've got a star that's here and you've got a distant star here, as if the Earth is moving around the sun, then where you would see that star would shift with respect to something distant. Now the only way you would not see this shift, this parallax shift, is if those stars were so far away that you couldn't see it. That is, imagine you're back in your train and instead of looking at houses or whatever that are going right by your window, there's a distant mountain peak. And that distant mountain peak just sits there as you drive or as you go around, right? That's why the moon looks like it's following your car, right? When you look out the window, the moon's always there at night. It looks like it's following your car. Because it's so far away, you don't have to turn your head to see it, even though all the local stuff is flying by you. So, and Aristotle understood this too. He sort of understood, yeah, in principle, if the things are really far away, much farther away than the distance between the Earth and the sun, then you could never ever observe this parallax shift. But that is ludicrous, because that would make the universe so big, it would just be unfathomably big. And then that idea was just dismissed. Are there questions about this? So what's really going on is, so Aristotle had something like this in his head. Not exactly, but the Earth is going around the sun, and you would see the position of this star relative to this star change. But what's really going on is that the stars are really far away. So as we move around the sun, we don't see it shift around very much. And in fact, the angular shift of the nearest stars is the equivalent of the width of a nickel at 6 miles. That was the shift that the ancient Greeks were trying to see by eye, and they could never see it. Today we can measure these kind of shifts, the parallax angles, very regularly. That's because we have very powerful telescopes that allow us to pinpoint positions of stars incredibly accurately. But obviously this wasn't happening in the days of Aristotle. Are there questions about this? Okay. So what this meant is that Aristotle's model matched a lot of data. It actually did a pretty good job of matching a lot of the things that were seen from day to day. But there was one thing that it didn't do well. the ancient Greeks are really obsessed with the idea of circular motion, and in particular, uniform circular motion. And so in Aristotle's basic picture, the planets went around the sun basically in circles, constantly moving circles. But if you very carefully track the positions of the planets in the sky, with respect to the background stars, they do something funny. Every couple years, for example, the planet Mars, normally, so let me just back up. Normally what the planets do, and the reason why they're called planets, planets means wanderer. If you look at the planets compared to where the stars are in the celestial sphere, the planets move where they are with respect to, say, the constellations, right? And this is somehow like the origin of a lot of astrology, okay? Like where, what, you know, in what constellation was Mars in when you were born and that kind of stuff. So the planets move with respect to the background constellations. That's why they're called planets. And that's why the Greeks knew that they were different somehow. Okay. The reason why they do this is because they're just closer to us. And so the stars are far away and they're closer to us, so they move with respect to them. So we see this over the course of time that like the position of Mars or Jupiter in the sky with respect to the background stars just kind of moves, whereas the rest of the stars stay fixed relative to each other. However, every now and again, the planets do something very weird. They don't just continue in one direction, but they stop, turn around, and do a zigzag and go forward again. That's called retrograde motion. And the ancient people knew this. They had tracked the stars very, very well. They had great star maps. And they knew that every now and again this would happen. And this could not be accounted for in Aristotle's model. So this was a problem. And it was particularly a problem because they were very concerned with astrology. They wanted to be able to predict, you know, what constellation Mars was in at any given time. This was important stuff. And they couldn't do it with this simple picture. So Ptolemy, who was who's basically a Greek, you can think of him as a Greek scientist living in Egypt at the time, probably the greatest astronomer of antiquity, or one of the best astronomers of antiquity, and he built an improved model that actually could account for all this stuff. And his model was kind of crazy looking, right? So Aristotle had this model where the Earth was in the middle and everything goes around the Earth on these circles. But Ptolemy said, well, that doesn't work, so I got to build something else. And of course, he still kept the Earth at the middle. And in order to get this backwards motion, he introduced something called epicycles. So like, for example, he put Mars here on this epicycle so that the center of it was like a loop within a loop, a circle within a circle. There would be a main circle that went around the Earth like this. But then on top of that circle, there was another circle that kind of wheeled around. And so that made Mars kind of do this loop-de-loop as it went around the Earth. Okay? And the reason why I did this is in certain times of the orbit, you would then see Mars do this kind of loop-de-loop pattern. Zigzag pattern. It would create the retrograde motion, and this is what he wanted to do. And remarkably, this model worked incredibly well. He had this very sophisticated loop-de-loop nested circle model that could tell you where the planets were pretty accurately for a very long time. And in fact, this model of the universe, okay, this Ptolemaic model of the universe, it looked like something like this. This model basically was the most successful model, the model that prevailed in sort of the Western world for 1,500 years. This was what basically people thought the universe looked like, with the Earth at the middle and this kind of crazy series of nested loop-de-loops all the way around. Are there any questions about this? Yeah.
So that was to explain the retrograde thing?
Yeah, so that is to explain, the reason why I introduced it was to explain the observed retrograde motion of the planets with respect to the background stars. Yeah?
So during Columbus's time, they did not believe the world was flat.
Very good, that's right, exactly. They did not believe there were. So that's kind of a weird myth that probably got started a couple hundred years after Columbus. But educated people living, you know, after Aristotle all believed that the Earth was round. I mean, there probably were some people who thought the Earth was flat, but the vast majority of people, in the Muslim world and the Christian world, the vast parts of the world all thought that the world was round. The thing that was debated at the time of Columbus was the circumference of the Earth. So Columbus had convinced people, or convinced himself, that the circumference of the Earth was tiny. And in fact, there were people living basically in the time of Aristotle who had already calculated the circumference of the Earth that was very close to what we see it now, but subsequent estimates made it small, and Columbus wanted it to be small. So he convinced people that the circumference of the Earth was so small that he could actually sail with ships of that day all the way to China by crossing basically the Atlantic Ocean. And so had North America not been in the way, right, Columbus would have died, because there's no way they could have made it all the way to China, right? So yeah, that was the deal with Columbus. It wasn't the round Earth, it was the size of the Earth. In fact, it's really interesting. I mean, there were Central Asian thinkers living in 1000 AD who very precisely calculated the circumference of the Earth and hypothesized the existence of North America. Basically, Al-Biruni, I think, was the guy who said, look, there's almost certainly that distance between this coast and that coast is so large, there's probably a landmass in between, and there's probably people living on that landmass, and in principle, we'll eventually go there. So there were a lot of people who even knew that there's probably a landmass there. So that story that's a whole story in and of itself. Anyway, great question. Okay, so we get to Copernicus now. So in around 1543, actually, at the very, very end of his life, Nicholas Copernicus published this idea. Now, he was a Polish priest, and the thing that was very interesting about Copernicus is he was one of the first people to have his own library. Okay? The printing press was just kind of coming into existence. Paper had made its way to Europe, and it was getting to the point where private individuals could actually have their own libraries to study in. This was a totally new kind of thing, right? Before, you had to go to these vast centers of learning that had books and scrolls, and you would learn from them. He had his own library, and he was he educated himself and was aware of a lot of this stuff. He was aware of the ideals of Aristotle and basically his enemies that thought he was wrong about the Earth being the center and not moving, etc. He knew, by the way, that Ptolemy's predictions were inaccurate in some ways. And he thought that Ptolemy's model was basically ugly. And he thought it would be much prettier to put the sun at the middle. And he knew that if he put the sun at the middle and had everything going around the sun, this could account for retrograde motion just as well as Ptolemy's model could. And I'll show you that in a second. But the problem was that when he did this, what he did is he put the sun at the middle, he made all the planets orbit the sun on circles. He put this whole thing together, and what he found is this didn't match the data either. And in fact, it did no better than Ptolemy. And this is probably why he waited to the very end of his life to publish his book on the revolutions of the celestial spheres, where he introduced this idea. Now, eventually, this Copernican idea would change the world, but it took a long time for people to accept it. There were feuding factions among the sort of proto-scientific community at the time. Some people liked it, some people didn't. But it did account for this retrograde motion in sort of a natural way. It's basically in the same way that if you're on the inside track, like the Earth, and you've got an outside planet orbiting the sun, sometimes you overtake them. And when you do that, you're first looking forward at them, and then when you overtake them, you look back. And so that's basically what's going on with the retrograde motion. Now, like I said, there's ideas of whether some people accepted it, some people didn't accept it. Interestingly, the English astronomer Thomas Digges was one of these heliocentric proponents. He liked the Copernican picture, but he actually got rid of the whole idea of celestial spheres entirely. So Copernicus had the stars still out there on a celestial sphere. Thomas Digges said, well, now that we've got this going on, let's just think of the other stars as distant suns. We'll get rid of the celestial sphere. All those stars are distant suns. And the reason why some stars are bright and some stars are dim is that the bright stars are nearby and the dim stars are far away. Kepler really kind of saved the day. So Johannes Kepler was a mathematician who was living around the year 1600. And he was working with data that was taken by another famous astronomer named Tycho Brahe. But what Kepler did is he said, look, the reason why this Copernican picture doesn't work, the reason why Copernicus's model of explaining where the stars and the planets should be in the sky at any given night is wrong, is because he's still stuck on this old Aristotelian idea that everything has to be on a circle. It doesn't have to be on a circle. And he put them on ellipses. He said, look, if you just make planets orbit the sun on ellipses, then everything works. And as soon as he had this realization, he broke out of this idea that everything had to be a circle. Suddenly, this Copernican idea where the sun's at the middle, everything now orbits the sun on ellipses, suddenly that works. Everything is taken care of, and we can start explaining the data incredibly well. And so for the really sober-minded people living at this time, this was probably enough to convince them that this model was better than Ptolemy's. But again, there was this whole idea of parallax that nobody could see. In fact, Kepler's boss, Tycho Brahe, was not a Keplerian. He thought for sure the Earth was fixed. And that's because he regarded himself as the greatest astronomer who had ever lived. He went out to look for this parallax, and he could never see it. And so he was on the side of Aristotle and said, look, the Earth is not moving because I can't see the parallax shift to the stars. So it's sort of debated. And this is how science works. People have an idea. People debate it. What about this? What about that? And the conversation develops from there. The final sort of nail in the coffin of the Ptolemaic / Aristotelian idea of what the solar system looks like came to us from Galileo Galilei. So Galileo was really an incredible kind of polymath type of scientist. He did lots of things, was really fundamental stuff in the very beginnings of physics. But the thing he's most noted for in astronomy, and maybe most noted for in general, was that he was the first human being to take a telescope and point it up at the sky. Now, the telescope was invented not by Galileo, but he heard about it. People had figured out that if you took two different kinds of lenses, okay, people were developing, it's a really interesting story. So people were developing lenses. People were starting to develop lenses in Europe. Why were they doing that? Because suddenly there were books in Europe that people were trying to read, and suddenly people realized that they were farsighted and they needed eyeglasses. So there became this huge industry for people to build lenses. And so people started figuring out how to build lenses. And some of the people who were playing around with lenses realized that if they put two of them together and lined them up in a certain kind of way, you could see stuff that was farther away than you could otherwise see. So the Dutch basically invented telescopes. Galileo heard about this and said, that's a good idea. I'm going to invent a better one. And he did. And instead of taking those telescopes and pointing them out to sea to look for ships, or pointing them at his neighbor's bedroom window to see other things, he looked up at the sky. And when he did that, he was the first human being to see a new star. He saw stars that no human being had ever seen, that had lived for the previous 100,000 years, because he had a telescope and nobody else did. And with this telescope, he basically revolutionized our view of ourselves. One of the really important things that he did is he discovered the moons of Jupiter. He showed that if you pointed his telescope at Jupiter, that there were these little dots that always stood near it. And if you tracked them, they actually appeared to orbit around Jupiter. This was a big deal, right? This demonstrated, look, there's other stuff up there in the sky that has stuff orbiting around it. And once you see that, it's not too hard to imagine a situation where not everything is orbiting around the Earth. He used his telescope to discover mountains on the moon and other things like that. But the thing he did to really fundamentally kill this Ptolemaic model had to do with Venus. Let me tell this quick story too. Kepler, as soon as he heard that there were moons around Jupiter, Kepler was a big fan of Galileo. They were sort of frenemies, kind of. They were rivals, but they were sort of both Copernicans. And Kepler heard about Galileo's discovery, and he immediately started speculating that Jupiter might have life. That was like the first thing he thought about. And from his point of view, he was like, look, God gave us the moon so we can look at it because it's so beautiful. Maybe that's why God put these moons around Jupiter. Maybe there's life on Jupiter so that they could see those moons. So he's sort of, taking ideas that he has and just sort of extending them out into the heavens. But the point is that these ideas of life elsewhere in the universe were immediately at people's fingertips. They were immediately thinking of them. But the real sort of nail in the coffin of the Ptolemaic model from Galileo had to do with Venus. And let me sort of walk you through this pretty quickly, but I just want to talk about this. In the Ptolemaic model of what's going on with Venus, okay, the little circle that Venus always orbited around near the sun was always in the orbit of Venus around the Earth in this model always had to be in line with where the sun was. And that's because it's just an observed fact that whenever you see Venus, it's either right after sunrise or right after sunset. That's just true, okay? And we understand that now because Venus is very close to the sun. And so when we see it, it's always sort of in the same part of the sky as the sun. But because of that, right, the sun was always only illuminating part of Venus. It was only illuminating a sliver of it and never of all of it. See what I mean? So if it's close to it here, so if Venus was over here and we were looking at it, you could see the full side of Venus lit up, and it would look like a full moon or a full Venus. But because in Ptolemy's model it was always partially lit, Venus always had to live near the sun, it was never getting full light from the sun. So it was always partially lit. See what I'm saying? Now that's very different than Venus in the Copernican model, right? Because Venus is going around the sun. So sometimes you see it fully lit up, sometimes you see it half lit, and sometimes you see it dark. So in the Copernican picture, Venus should go through phases. Whereas in the Ptolemaic picture, it shouldn't. It should always be a crescent. Right? Now the problem is, prior to the telescope, you couldn't tell whether something was a crescent or fully lit up. It just looked like a dot in the sky. But now Galileo has his telescope, and so he can say, look, do I see this or do I see this? And he looked, and he saw this, right? And that immediately killed this. We're done. Okay? So any rational person who wanted to argue about, well, I don't think the Earth's moving, blah, 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 whatever, it's not doing this. Okay? This Ptolemaic picture cannot possibly work because it predicted this, and this was not seen. This is what the scientific method is about. Okay? This is what it's about. You have theories, you have ideas, you make predictions, you test those predictions, they don't come true. You have to throw your theory out or at least modify it in some way. Questions about this? Okay. So these phases of Venus are seen now, and that's a big deal. Finally, sort of the last and kind of ending piece to this story comes from Newton. So in 1687, Isaac Newton published this book called the Principia Mathematica, and it's widely regarded as the greatest work in the history of the physical sciences and arguably the greatest work in the history of all sciences. But I'll talk about Darwin in a second, and so then there's some rivalry there. But you know, it's up there. In this book, he actually derived the law of gravity and showed that with his law of gravity, he could explain why all the planets orbit the sun in ellipses and why they have to. He could explain the origin of the tides on Earth. He could explain why the comets will come back periodically and when they will come back. Fundamentally, the thing about this book that's so important is he demonstrated that the same physical laws that govern apples falling from trees on Earth govern the orbits of the moon and the planets around the sun all throughout the universe. So in principle, the same physical laws act here as they do everywhere. And this was like very much anti-Aristotle, right? This is not what Aristotle was preaching. So this marked a very important revolution, this Copernican/Newtonian revolution, was very important because, number one, not only do we orbit the sun, but it means that the universe is much, much, much bigger than anyone thought possible, because we don't see that parallax shift of the stars. Okay? Aristotle was wrong. Admittedly, a smart person, very, very smart, but the old ideas aren't always right. And when you're faced with new data, you can change your mind. And sometimes you can change your mind for the better. People are capable of figuring things out that seem to defy common sense. But by a progression of logic and observation, and eventually sort of mathematical rigor, you can figure out a lot of very complicated things that don't seem reasonable at first. And immediately, the proponents of the heliocentric theory started to think about life elsewhere. So let's bring us back to this course, right? So our place in the galaxy then becomes one star among lots and lots of other stars. And we're starting to think about how then we fit in to this world. We're zooming back into the galaxy from this movie I was showing in the beginning. Eventually, we're going to zoom in here to, let's see. We're going to zoom in on the sun. Okay? We're going to dim it out so we can actually see stuff here. This is artificial dimming. Finally, we get to the orbits of the outer planets here. I'm going to zoom in to our little planet. We're the third one in. Right there. Okay? It's really amazing to think just how teeny tiny we are. This circle here, that's the orbit of the moon. We still can't see the Earth. Okay? There it is finally. We'll zoom in on it. This is the dark side, nighttime over here, daytime over here, the sun's over here, and that's where we're looking. Oops, yeah. So this little dot, this blue little dot, is the only place in the universe where we know that there's life. And so this is where we start. But before we start looking for life, we need to define life. What is it that we're looking for? Okay, so if I were to do a poll, if we had some clickers in this class, I'm pretty sure which one everybody would click. All right. Hello Kitty is beautiful and everything, but probably this one is alive, right? So distinguishing alive from dead is sometimes easy. You know, inanimate and animate, that's sometimes easy. But you know, sometimes it can get a little harder, right? So which of these is alive? What about these? So the question is, what's the line here? And how would we go about defining it? So viruses, for example, are considered by many biologists to be sort of at the dividing line between living and non-living things. Because viruses cannot replicate on their own. Within their species, they have to invade another cell to have replication. But this is sort of subjective, but that's sort of the point. But we don't know exactly how to do this. Okay? Our old friend Aristotle had some ideas about how you might define life. He said, well, life is something that grows, it maintains itself, and it reproduces. But there's always sort of counter questions. Like you could say, well, what about fire? Okay, fire grows, it maintains itself, and it reproduces. Is fire alive? What about mules? Okay, mules seem pretty alive. They can't reproduce, but, you know, seem alive. There's a really interesting idea that comes to us from the world of physics, specifically Edward Schrödinger. So Schrödinger is famous sort of for developing quantum mechanics, one of the very famous physicists of the 20th century. He said life, you could define something as being alive in physics, is if it's something that decreases or maintains its entropy. Okay, and entropy is a physics word that I'll talk about in a second. It evades decay from equilibrium. Okay? And so this idea of entropy is something that physicists talk about to describe the tendency for the universe to become more disordered naturally. Okay? So entropy is the thing that it always tends to increase with time, or at least not get smaller. This is the reason why, for example, if you see a movie, like if I were to take a cup and drop it on the floor, it shatters into a million pieces. Okay? Now, if I were to show you a movie of that, you would say, okay, fine. But if I were to run that movie backwards, that seems wrong, right? Somehow you've gone from this cup that was all broken up into something that's all put together. And the reason why that sort of seems wrong to you is that the entropy is flowing in the wrong direction. You're taking something that's extremely disordered and becoming ordered. So it doesn't matter, you know, it's possible to take something that's disordered and make it ordered, but it requires an external actor. It's not sort of the natural flow of things. Okay? So what Schrödinger was saying is that this idea of entropy, so entropy you can think of it as disorder, progressing through a disorder. Life is something that actually, through its own process, maintains this order. And if anything, makes things more ordered over time. And so you could think about things as a physicist and just say, so if we look for something, we're looking for an internal decrease in entropy or maintaining its entropy. And there's a lot of work being done right now sort of in mathematical circles thinking about life in this way. It's a really interesting direction. I mean, I'm not going to talk about it anymore in this course, but just sort of introducing you to ideas. Another approach is sort of the I know it when I see it approach to life, like we were doing with Hello Kitty there. And this comes from the famous Potter Stewart quote. I don't know if people have heard this before. This is sort of in the 64 US Supreme Court case where he defined pornography as something that he knows it when he sees it. Okay? I'm not going to try to define it. I'm just going to know it when I see it, and that's pornography or whatever. Okay? And you can take that approach with life if you want. This is all well and good, but you know, how are we actually going to, we need to work here. We need to do something, so how are we going to do it? So another approach, sort of a practical approach that people have taken, is to introduce a number of necessary but not sufficient criteria. Okay? A number of criteria that are all necessary for life but not sufficient for life. So what do I mean by that? What do I mean by a necessary but sufficient criteria? So let me give you an example of that. You can't win if you don't play the lottery. Okay? So a necessary condition for winning the lottery is playing the lottery. Is it a sufficient condition for winning the lottery? No. Right? So a necessary but not sufficient criteria is sort of something that's required, but having it doesn't make it so. Okay? So basically, there are 6 characteristics common to all living organisms on Earth that people use to characterize the definition of life. For example, there's order and structure. There's the ability to reproduce, the ability to grow and develop. This is an important one, to utilize energy from their environments. Okay? So life doesn't just happen in the absence of energy, right? Life requires energy to do something. So energy is the capacity to do work. So without energy, you can't do anything. You can't live, you can't grow. And so utilizing energy from the environment is a really important thing about life that we'll return to. On the Earth, the primary energy source for life is what? Does anyone know? The sun. Very good. The sun. Right? The energy from the sun is what plants use to grow. When animals eat plants, they get energy from eating those plants, but the ultimate source of the energy in the plants is the sun. And when we eat animals or plants, it's the same thing. Ultimately, the energy source is the sun. So for most life on Earth, although not all life on Earth, the primary energy source is the sun. Life responds to its environment, okay? And it evolves to adapt to their environment. And this is another key one that we'll focus on. So let's start with the first one just for, again, necessary but not sufficient conditions, order, right? You can't just have a disordered thing blob and that be alive. You need some order, right? So you need, you don't have molecules that are just random, but they tend to have coherent patterns or structure. But of course, order is necessary but not sufficient. You have this beautifully ordered snowflake over here. Most people don't think snowflakes are alive, but it's sort of reminiscent in its orderliness to flowers. Reproduction is another one, right? But you know, it's still a cloudy area because viruses and prions, for example, are these borderline cases between life and non-life because of their sort of reproductive habits, right? So viruses don't reproduce on their own, right? When we get a virus, that virus is hijacking our cells and then using our own cells against us to reproduce, right? Prions are also infectious proteins, okay, and they reproduce by basically changing normal proteins to do their weird, you know, to act like they do, to act abnormally, right? So this is a mad cow disease, for example, is a disease that comes about because of this prion activity. So you know, it's sort of this like dividing line here. One of the really important things, the sort of sixth step, was evolutionary adaptation. And I want to take a minute here to sort of end this. You know, we've got about 15 minutes left. Let's talk a bit about evolution, because obviously evolution has fundamentally altered the way we think about life and the origin of life and progression of life on Earth. Okay. Evolutionary adaptations accrue in populations. Okay. They don't accrue in individuals, but they accrue in successive generations, right? But after a while, enough successive variations can create a whole new species. So this is just a simple example. You've got, you know, a rabbit that lives somewhere where it's green, and here we've got a rabbit that's living. The snowshoe hares have these seasonal camouflages. So when it's green, it has this, and when it's snow-like, it does this. This is an evolutionary adaptation to keep it hidden. Now, this idea of evolution has actually been around a very, very, very long time. Okay? Anaximander, who was living way before Aristotle, you know, this is Thales' student, you know, it was at the very, very dawn of sort of scientific thinking. Anaximander basically said, look, life arose in the water. That was his theory. Life arose in the water, and it developed into more complex forms after rising out of the water. Does that sound familiar? It's amazing, right? Aristotle said, nope, that's nonsense. Species are fixed and unchanging. And you know, Aristotle was a pretty convincing person, and so basically Aristotle won. But not based on direct observations or anything, right? Erasmus Darwin, not Charles Darwin, but his grandfather, was very interested in this idea of evolution. There's a quote: "The strongest and most active animal would propagate the species, which should then become improved." So this idea of you have the strongest animal survives, and the next generation is also strong. So this basic idea that there could be evolution in that way had been around. Okay? Of course, Lamarck, who's sort of a kind of contemporary of Darwin more, he thought that traits were acquired by organisms during their lifetimes and then passed on to their offspring, right? So, you know, if I cut my hand off, it's more likely my child will have no hand, sort of idea. Or, you know, if I am Arnold Schwarzenegger and I get to be really strong by lifting weights, then my kids will be really strong. That's also wrong. We know this is wrong now. But the key insight that Charles Darwin had, right, was that it was natural selection as the primary mechanism for evolution. Okay. Now, this book that he wrote, Origin of Species, in 1859, was incredibly influential because he wrote it in a way that people could read. This is different than Principia Mathematica, by the way. Reading Principia, you basically have to be like a professional physicist to follow it. It's incredible the stuff he was doing there. But Darwin, you know, wrote this really nice book that's easy to read. You know, you can read it. And it sold very well and was incredibly influential, this idea. Now, Darwin knew, for example, that about artificial selection. People have been doing this for thousands of years. Okay? you can breed animals for favorable traits, and their offspring will be more like that, right? So, you know, these are sketches from Darwin, sort of thinking about variations of animals. But a more familiar case, right, are the dogs that we have all around us today, right? All dogs have a single sole ancestor, which is the gray wolf. So through manipulating, like breeding the ones that we want to breed, like we've created this thing and this giant thing, right? Just by breeding the ones that sort of get the two big ones together, and you know, eventually you make these, right? So it's crazy, it's amazing what you're able to do over generations, not even that many generations, if you think about it. We also, of course, do it with plants, okay? So wild mustard, okay, is the sort of thing that eventually gave rise to broccoli, cauliflower, cabbage, all this stuff. And they're all descended from wild mustard. But this is not natural selection. Here it's humans who are the agents that are creating this process. But you could see if there was some other mechanism that acts to select, all kinds of stuff could happen. It doesn't have to be humans doing the selecting. So Stephen Jay Gould has said the following, which I think is very useful way of seeing it, is that natural selection, the idea of natural selection, is based on two undeniable facts and one inescapable conclusion. And the first fact is that any population can produce more offspring than its environment can support. And this will naturally lead to competition for resources. Not everybody's going to get water. Only a subset of the population is going to get water. And that population is going to live. The other one's not. And by live, I mean reproduce. Fact number two is that individual offspring vary in traits passed from their parents through the mechanism of heredity. Now, Darwin did not understand what the mechanism of heredity was in a microscopic way, but he understood that there was such a thing as heredity, right? And it's pretty obvious to all of us. People pass down their traits to their offspring. Animals pass down their traits to their offspring. Like that happens. Okay? So the inescapable conclusion is that those individuals whose traits best adapt them to survive and reproduce will pass on those favorable traits to a larger number of offspring. Right? So you have some randomness. So that's the sort of part we haven't really discussed. But you have a population of things that emerge. And there's some randomness in their traits. They're similar to their parents, but not identical to their parents. Some of you are thinking, thank God. But you're not identical to your parents, but you've got some traits, but admit it to yourself now, you're like your parents in some ways, right? But you're a little different. And so there's variation. Every generation has some variation. And if there are little variations that give you a slight edge in times of limited resources, you're going to be much more likely to survive and pass that specific trait that gives you that advantage on to your offspring. And so it goes. Right? So that's the idea. I mean, you can see this in action, right? So for example, there are white clover plants. And there are some white clover plants that have, by heredity, evolved the ability to produce cyanide when they're crushed by a cow's teeth. So a cow bites them, a little cyanide comes out. Those cows that like to eat those kind of plants aren't going to make it, right? And that's good for the plant. But, unfortunately, cyanide is also released when the clover freezes, and that kills the plant. So that freezing kind of acts like being chewed by a cow, and that kills you, and you don't want that to happen. So what happens? So amazingly, right, is cyanide production a favorable trait or not? But amazingly, if you look at a map of where you see the cyanide clover, okay, and the non-cyanide clover in white, the cyanide clover is places where the winters are warm and they don't freeze. And then it makes much more sense to be, unattractive to cows than worrying about whether it's going to freeze or not, because it never freezes. However, if you die every winter, then it doesn't matter whether or not cows want to eat you. So that's not a favorable trait, and so you don't have that trait. Here's another thing that's very, very interesting, and we'll talk a bit more about the fossil record, et cetera, et cetera. But if you dig down into the Earth, as we'll talk about later, we think that the Earth is kind of stratified in age and depth. So as you dig down, we're seeing older and older layers, more or less. It's complicated, but that's basically the case. If you go way down to ages to depths that correspond to about 500 million years ago, that's when you first start seeing animals with heads. But then above that time, a little later, a couple hundred million years later, it's where you see everything with heads and limbs. So now you see heads, some things with only heads, and some things with heads and limbs. If you go a little bit later, you see things with heads and limbs and hair and breasts. But you only have to get up to very close to today before you see things with heads and limbs and hair and breasts and walk on two legs. So these sort of general characteristics of life appear to take time to evolve. So you see it. And you can see even the evolution of from fin bones to arms. You can see them traced out also in the fossil record. So it's really amazing. Is that a hand, or are you just stretching? Okay. Stretch on. Okay. Are there any questions about this? Okay. Okay. So with all that in hand, we've basically got what we're going to treat as a working definition of life. Okay. Living organism is something that can reproduce and evolve to adapt to its environment, and that's where it is. That's a pretty broad, open statement for life, but I think we probably need to be pretty generous when we think about life beyond the confines of Earth, because it could be lots of different things. All right, we'll get at it again on Tuesday.